you may not have been taught this, but differential equations they're really all throughout science and engineering. So you learn calculus, integrals and derivatives are very useful, very important. But when you get into engineering and advanced science and advanced, physics and things like that, chemistry and other things, then most processes in real life really do obey differential equations. And so in a nutshell, and I'm going to write it down in a minute, but in a nutshell, a differential equation, just pick the word apart. What does it mean? Differential. Think about calculus. Differential. dx. Differential. Little small value of x. Or derivative is what comes to mind when you think of differential. So differential equation is just simply an equation that involves a derivative. So a normal equation, like from Algebra 1, a normal equation might be, x plus 3 is equal to 4. And you know how to solve that equation. You know that the goal of this equation is to solve it for the unknown value of x. That's what you already know because you've done algebra, right? And you know how to do that. You pull the 3 over and subtract and you get the answer, right? Well, a differential equation will not involve the value of the unknown x by itself. A differential equation might involve the derivative of x. Maybe with respect to time, let's say. Plus 3 is equal to 4, right? So this equation, the second one here, congratulations, you've just looked at your very first differential equation. It's just simply an equation. It has numbers, has an equal sign, it's plus, that's just like an equation. But instead of x, it's the derivative of x. So ultimately what we're trying to solve for here is x. That's the thing you got to realize. This equation is a derivative, and ultimately when you solve it, you are still trying to find the value of x, right? But obviously x is wrapped up inside of a derivative here, so it's a little bit harder to get at. And so we're going to learn about the different ways in which you can do that. So that is what a differential equation is. It's simply an equation that involves the variable that you're hunting for. And so what you're going to find out, though, in this section will be not too bad to solve for because it's an introductory section. But what you'll find out is that when you get into real differential equations, you can't simply solve for x like that. You can't simply just isolate the variable and take an integral and get the answer. It just doesn't, you'll find out when we get there that you're not going to be able to do that. But we're going to crawl before we can walk, and so we're going to take some easier problems first. So in this introductory section, I want to show you a differential equation that every one of you guys have probably seen. I would venture to guess that everybody has seen, and that is the famous equation F is equal to ma. Force is equal to mass times acceleration. Now, this does not look like a differential equation because you don't see a derivative in there, but it is a differential equation. And for those of you who think hard enough, you'll realize that this is a differential equation because this acceleration, the thing that we call acceleration, is really a second derivative of position. So in physics, they don't really go into this differential equations business because it's too complicated. It burdens the material too much for a freshman to soak up differential equations on top of soaking up the physics. But now you've reached a point in your learning where I'm going to tell you that some of these things that looked so simple before were in fact really differential equations. So let's look at this some more. If I take this equation and I solve for a, the acceleration, which we know ahead of time is going to be basically a derivative, then this acceleration is equal to force over mass, right? We just solve by dividing by m, so that's the acceleration. Now, this, for any given problem, is just a number. Just a number. In my particular case. Because I'm saying, what if I have, a 10 kilogram mass, and what if I push him with 50 newtons of force? So I can take the 50 newtons of force and the 10 kilograms, divide them, and what I'm going to get on the right-hand side is just simply going to be a number for whatever problem I have in front of me. The acceleration, the thing that describes the motion, is what I'm really mostly interested in these physics problems, and of course I'm teaching it here as well. So the one thing that you need to realize is that the acceleration, A, the thing that we call acceleration, is simply the derivative of the velocity of something with respect to time, the change in the velocity, the change in the speed, right? And the velocity is also the change of position. So when you put all those two things together, the acceleration is the second derivative of the position with respect to time. And so this little indication here, you know, from calculus with the 2 there, that means second derivative. So this is just saying in words what I already told you, is that the acceleration is the second derivative of the position. Because if I draw, you know, a meter stick here and I watch a marble traveling down there, if I look at how far it goes in a given time, that's the first derivative, the change in position with respect to time. That's going to be, well, the change in position with respect to time, that's going to be the velocity. If we take the derivative again, the change in velocity, we get what we call acceleration. I think we all have a pretty good idea about it because we drive cars and we accelerate. All right, so when we use this information, we put it all together, then what we're going to do is take this guy, and let's bring him down here. So we will say the acceleration is simply the second derivative of the position with respect to time, right? And that's equal to F over m, which we just said is a number for whatever problem I'm using. So really, when you think about it, I could just spit this out and show you this and say, ladies and gentlemen, this is a differential equation, and this thing right here might be 10. Because it's the ratio of the force to the mass of my object, or it could be 15, or it could be 19. So the differential equation here is, you know, d squared x dt squared equals a number. That is a differential equation. It happens to describe the motion of an object of a certain mass, and you push it with a certain force. And so obviously when we solve it, this is the acceleration, and we want to end up at the end of the day figuring out where this thing is. So we want to solve for x. So the whole course of differential equations is you're going to have lots of equations that are going to have derivatives of some variable with respect to either time or something else, usually with respect to time, but a lot of times it'll be with respect dy with respect to x or something. Anyhow, you'll have a derivative of something with respect to something else, and the goal is to calculate a function of this variable, x of t. That's what we're looking for in this case. So our solution, you know, might be x of t, you know, is equal to, you know, 2t or something. I mean, that's a function of t. I mean, that's not exactly what it is, but it could be something similar to that. All right, so congratulations. You've learned that something you've learned in physics long time ago is actually a differential equation. Now, how do we solve it? How do we solve this simple one? First of all, before we get to solving it, I want to show you a few things about this equation. So this is an ordinary differential equation. And I'm going to write this as diff EQ, however you want to pronounce this. That's how I abbreviate differential equation. That's way too long to keep writing out. The reason it is called ordinary, this is the word I'm going to underline, is because there are no partial derivatives. All right, no partial derivatives. So you need to memorize that because the course that you're taking right now, it may be called differential equations, your first course in differential equations, but really it should be called ordinary differential equations. Ordinary just simply means it's a straight derivative with respect to something else. There's no partial derivative of x with respect to time. The only time that you would ever have a partial derivative running around a function is if this function, if this variable here that you actually have wrapped up in your derivative is itself a function of two variables. And that actually is really common when you get into real world problems because we live in a three-dimensional world. So let's say I have a block here, a brick, right? And I may have a flame underneath it heating up the brick. And obviously the flame is on the bottom, so the bottom of the brick is going to be absorbing the heat, you know, a lot more than the top of the brick. And so the heat transfer, for those of you who are, you know, mechanical engineers or chemical engineers, the heat transfer, really the function of the heat is coming from the bottom and it's propagating throughout this brick coming up to the top. And it's a three-dimensional problem because this flame is like a point, right? And this block is this big thing over here. So obviously the heat transfer in the different directions is going to be different. It also depends on the material, how much heat is transferred is a function of what the material is too, but it depends upon, you know, where this heat source is and what direction you're looking, because, you know, here very near the flame, you might have different heat transfer than, you know, farther away at the top of the brick because the heat source is at the bottom. So in real problems, in real life, with three dimensions, it's very likely that whatever it is you're trying to describe, in this case I call it X, it could be the heat transfer, you know, through a material. Or it could be the electric field in empty space, right? Or something like that. The real description of that guy is always going to depend on three dimensions, unless you have a perfectly symmetrical problem, right? And so in those cases, maybe it's okay to just talk about one variable, but most of the time it's going to depend on more than one variable. So in those cases, you'll have a partial derivative to describe how the thing changes in this direction. And you'll have another partial derivative to tell you how it changes in that direction. And you'll have another partial derivative to tell you how it changes in that direction. If you have a differential equation with partial derivatives in there, it's called a partial differential equation. It's not called an ordinary differential equation. So that was a long-winded way of saying everything we learn in this course is going to be ordinary differential equation. You'll never see a partial derivative anywhere in this course because it's a more advanced topic. It's more complicated to solve even than these other ones we're going to learn in this course. You'll always see straight derivatives with respect to one and only one variable because the function that you have and that you're studying is only a function of one variable, right? And so that's what we're going to study in this course. All right, the second thing I want to point out to you, so I'll put a little thing here. Second thing I want to point out to you is this ODE, and that's another word I'm going to, or a little abbreviation I'm going to put that you'll see in your book, ordinary differential equation. That's what it means. This ODE is second order. It's of second order. This one here is what I'm talking about. And the reason it's of second order is because the highest derivative, deriv means derivative, the highest derivative is equal to 2. Right? So this is what you have here. This obviously isn't squared. This is telling you that this is the second derivative of x. That's the highest derivative in this problem. And so this is a second order differential equation. Now you might guess that the higher order differential equation that you have, the more derivatives that you're taking upon this variable, the more complicated the problem is going to be to solve. Exactly true. And it'll take a lot longer to solve problems that have higher order derivatives. So in your test, you'll probably be asked, what order is this equation? So it's very simple. You just look at all the derivatives, whichever one has the biggest number as the highest derivative order that you have, that's the order of the equation. So 2 terms. Ordinary differential equation means no partial derivatives anywhere, that everything in this class is going to be that way. And the order of the differential equation is just given by the derivative. So, in the course that we're embarking on here, we're going to spend a great deal of time talking about really simple equations first, with just one derivative, first derivative. In this case, because this is an equation everyone has used and come to know and love from taking physics, it's very, I think, interesting and cool just to work with this one for a second. Even though it's second order, and even though that's a little more complicated than what we're going to get to in the subsequent sections, let's go ahead and work with this one, because I think that it'll really open your mind to that this stuff is very easy to kind of comprehend conceptually. So let's go ahead and work with this. How do you think you would solve this equation? How do you think you would solve this equation? Well, you should know back from calculus, just like from algebra, you always have to think in equations. In algebra, the opposite of division is multiplication. The opposite of addition is subtraction. The opposite of, cubed root is to raise something to the third power, right? There's always an opposite that you could apply to something to cancel out and isolate the variable. In calculus, the opposite of a derivative is an integral. You know that. And the opposite of an integral is a derivative. So we should be able to simply integrate this equation a couple times, 2 times to be exact, integrate it, and then that will isolate the variable off by itself. Now notice that we're only able to do that because this equation is so simple. It's got the derivative over here, and then it's got what's going to amount to be a number over here on the right-hand side. So yeah, of course I can integrate that, but if the equation were more complicated, if I couldn't isolate, what if there was another derivative over here? This one plus a first derivative, then I wouldn't be able to integrate it. It would be more complicated. But if you have a problem that you simply have a derivative on one side and some other junk on the other side that's just a function of t or a constant, then you can just simply integrate it as many times as you need to get back the function that you have. And that's what we're going to do. So let's move over here and let's rewrite this. So let's say in this problem that the second derivative of x with respect to t, let's just say in this problem that that's equal to 30. Because, force divided by mass, whatever the force is I was pushing, whatever the mass is of the object, I don't care about the individual things. I'm just saying that the division of these 2 things is equal to 30, just so I can have some kind of numbers to work with this problem. Now, obviously, it's going to depend problem to problem what that is, because you may have a different size ball or whatever. But for this problem, we're just going to choose the number 30. So in that case, what this basically means is that this differential equation in all of its glory is exactly written, we need to write it again, it's exactly written the way I have here. Second derivative of x with respect to time is equal to the number 30. So how do we solve for x, the function x of t? So what we're going to do is let's apply one integral, d squared x dt squared. And we're going to integrate with respect to time. And so we have to do the same thing to both sides of the equation. So we're going to integrate with respect to time. So you see what we're doing here. This is a derivative with respect to t. So we integrate with respect to t, and that should get rid of one of the derivatives for us. Whatever we do to one side of the equation, we have to do to the other. So we again integrate the right-hand side with respect to t. You have to do the same thing to both sides. And so what we're going to do here is we're taking an integral of a second derivative. And so when we do that one time, what we're going to get down here is we're going to simply get back the first derivative, dx dt. Because integrals and derivatives are opposite of one another, so if we take the integral of a second order derivative, we're going to get back a first order derivative from that. It's sort of your basic calculus here. On the right-hand side, we're going to integrate this constant. It's a very simple integral. It's going to be 30t plus, and I'm going to label a constant of integration here, because we always have constant of integration, I'm going to label it C1. Now in Calculus 1, Calculus 2 even, usually when you have a constant of integration, you just label it C. C is the constant of integration. But in differential equations, I encourage you to always label it with a number 1, and then again, if you have a second one, number 2, number 3, and so on, because I'm going to eventually here in the next step, we're going to integrate this whole thing one more time, and we're going to get a totally separate constant of integration for the subsequent operation. So you need to keep them separate, and you'll see why we need to keep them separate, here in a little bit. So do yourself a favor, label it constant 1. Next time you get a constant, label it constant 2, constant 3, constant 4, and so on. So here is sort of an intermediate step. Now here's a bonus question for you. What order is this differential equation? Because this itself is a differential equation. It is a derivative of x with respect to time, and here's a function of t. This is a first order differential equation because this is a first derivative. That's the highest derivative in the whole thing. And by the way, here in the next few sections, we're going to spend a huge amount of time just learning how to solve first order differential equations, because this is a simple one, but there's a lot to it, and there's a lot of different techniques, and we're going to learn that before we move on to higher order differential equations. I'm just messing around here with the second order because I think it's going to teach you a lot. You'll learn a lot from it, especially since it comes from F equals ma, which everyone's seen before. So what we're going to do now, you probably have guessed, is we're going to take this guy and we're going to integrate it. We're going to integrate him again. So let's go ahead and integrate dx with respect to time. We're going to integrate with respect to time just like we did before. We have to do exactly the same thing to the right-hand side. So it's going to be 30t plus c1, and that's going to be dt, right? We're going to integrate both sides with respect to time. Now, over here, it's very simple because we have a derivative with respect to time. We integrate it. We're just simply going to get back x. Don't forget, though, that x is a function of time. That's the whole point. Everything that we have in this class is going to be a function of time, because you know it's a function of time because you took the derivative. This is the derivative of x with respect to time. So when we get the answer, let's go ahead and remind ourselves that x is really a function of time, and we'll put it just like this. Now, on the right-hand side, this integral is pretty easy to do. This will be 30 over 2 times t squared for this term, simple integral, plus, and over here what we're going to have is c1 times t, because this is a constant. It's just a constant. It could be 5, it could be 7, we don't know. So we're just going to put that with the t there. That's a simple integral. And then, of course, you need another constant of integration. So we're going to call that one c sub 2, and that's why I told you that when you're doing your constants of integration, always make sure and label them C1 and C2, because this is a totally separate constant than this one. And we're going to be using those, so don't mess that up. So at the end of the day, let me try to switch back to black here. At the end of the day, what we got for the answer to this guy is a function of time, which was 15t squared plus some constant times time plus some other constant off by itself. This was the answer to what we got. 15t squared plus c1 plus c2. This really is the answer to the problem, right? So what we started with was a second order derivative is equal to a number, and what we got at the answer was we solved for x, and of course x is a function of time, so you know that's what we have here, because you know motion is always going to be a function of time, so it sort of makes sense. Now notice that it looks a little bit weird though, because there's still these two constants laying around here. Here's the deal with differential equations. This guy, this solution right here, is called a general solution to this differential equation. And I'm going to write this down here in just a second so you have it burned into your head. You're going to need to always remember these terms. So this is called a general solution because it describes all possible solutions that are possible for this equation. The reason it describes all possible solutions is because you have these two constants here. These two constants could be anything, really anything at all, and whatever numbers you put in there, it's going to satisfy this differential equation. So that's a general solution. Now the reason why it's called a general solution is because, you know, in a real world problem, when you have motion of an object, it's not really good enough to know all possible solutions. We're usually interested in finding out what the specific solution is to our problem. When we throw a baseball, how far is it going to go? What is its acceleration? What is its velocity as a function of time and all this stuff? So in order to know that stuff, you know, this is describing sort of the general characteristics of the motion, right? Or of the position as a function of time, right? But in order to get the specific solution to our specific problem, we have to always talk about our initial conditions. Did we throw the ball? You know, did we just drop the ball? Did we, you know, start the ball off with a very fast velocity, or was it starting off with a really slow velocity? And though that piece of information, which is going to come from our initial conditions, which you're going to hear all throughout differential equations, the initial conditions of the problem, that's going to tell you the specific solution to the problem. So let's go ahead and write these things down and burn it in your mind, because they're very, very important. So this guy, I'm going to put a little arrow here. This is the general solution to this ODE of this ordinary differential equation, right? And the reason is because there are infinite, I'm going to put infinity there for infinite, solutions expressed here. Which correspond is going to be correspond to the values of C1 and C2. This is expressing in words exactly what I told you. C1 and C2 are basically going to be defined by whatever initial conditions you throw this ball with, because this is a question that talks about motion. So it's all going to be about how do you start the motion off. Because, you know, if you think about it, you know, this is gravitational field that I'm standing in, right? So I have this pen, and I drop it from here, right? So we know there's a differential equation that governs this, because F equals ma, I just taught you, was a differential equation. So I could go through a problem and show you that that's the guy here, right? So I would, if I did that, I would calculate a, you know, function of time that was general in nature, that had these constants in there, and those constants would be defined by how the motion started. So this is one motion. This is one profile of the motion when I start the guy off with zero, position of zero, velocity of zero. When I start the clock, he begins to move. So this is one profile of the motion that might be described by this equation that we solved for here. Now let's say I have a different set of initial conditions. Let's say I throw him in the down direction. So I throw it down harder. So at time is equal to 0, he has a very high velocity. Well, obviously this is a different motion. He's going faster and farther as a function of time. So the initial condition, the initial motion that I gave him dictated sort of it would dictate a different answer. So these constants here, I'm going to teach you how to calculate them in a second. They're going to depend on the initial conditions. Another set of initial conditions might be, maybe I throw him up, right? So I throw him up. So instead of a downward velocity, he might have an upward velocity. So it's a totally different motion. But the general solution to this general equation of F is equal to ma is always going to be the same. These constants are going to be totally different depending on the initial conditions of that problem. So that's enough of talking about it. Let's go ahead and make a little bit more progress. So let me write one more thing down, and I'm going to put him in a different color just so we don't, we don't get cross-eyed looking at this. C1 and C2 are determined by two initial conditions. Are determined by two initial conditions. Whoops, let me spell conditions correctly. Conditions. All right, if you change the initial conditions, then you change those constants, and your final answer would be totally different. And that's exactly what I was teaching you. Different initial conditions are going to yield a different profile of that motion, which would correspond to different x of t. And that's going to all come about through these different constants. Now, let me show you one more thing. In this case, for this example, it's going to be the initial position and velocity. Those two things are going to correspond to C1 and C2. So if I have a different initial position and a different initial velocity, then C1 and C2 are going to be different. And so then x of t, when you plug C1 and C2 in here, is going to be a different equation. It's going to be a different parabola that it's following, or a different second degree polynomial here in t, right? If I have different initial conditions, then my motion is going to look different, which is what we all know. But the general form, this guy, the general form is going to be given by this, because there's infinite solutions expressed here. Depending on the infinite number of ways I could begin to throw this marker. The different positions I can start it at, and the different velocities and directions and all that stuff is all wrapped up in here. All right. Very important. That's why I'm kind of harping on it so much, because it's very important for you to understand that all differential equations, all of them, are going to yield a general solution, which is basically infinite number of different solutions. The specific solution to your problem is going to depend upon the initial condition. So we're talking about velocity here, position. So the initial velocity, the initial position is going to be our initial conditions. But if we're talking about, the electric field, let's say, you're calculating, and that was governed by differential equations, which, by the way, they are, then your initial conditions might be the initial field strength and the initial field direction, right? Or maybe if it's a heat transfer problem, your initial conditions might be, and you're talking about the fluid, the heat flow through a material, then your initial conditions might be the initial heat flux and the temperature or something like that. Depends on your problem. It depends on what you're setting it up to do. But your initial conditions are going to be specific to the problem that you have. And you're almost always going to calculate a general solution first and then zero in on your specific solution. So let's do that here. So let's recap. The general solution to this differential equation that we have is x of t, whoops, wrote that wrong, x of t is equal to 15t squared plus c1 of t plus C2. So this is a solution to differential equation. You know it's a general solution because it has these constants in it. That's all you really have to remember. Now, if you want to find the specific solution to your problem, you must know what the initial conditions are, and those are usually given to you in your problem, or given to you on the test, or if you're practicing in the real world, or given to you by whatever your problem is. So let's say the initial conditions are given by the following. The initial position, let's say, x at time 0 is equal to 0. And that's meters because this is position. And let's say the initial velocity is x prime of 0 is equal to, let's say, 1 meters per second. You need to get used to seeing it written this way, because this is how it's going to be written in your problems. What this is saying is, don't forget, this is a function of position. That's what it is. X of t is position. So what this is saying is that the position at time 0 is equal to 0. It just simply means that if I have a tape measure here and I'm looking at the rolling of a marble along it, then at time 0, the marble begins at location 0. So the marble begins over here at the end of the meter stick. That's all it means. At the time of 0, that's where it is. Now here, x prime, that's, don't forget from your calculus, a little prime there, that means that is a first derivative. So derivative of position's velocity. So what this is telling you is the velocity at time 0 is equal to 1. Don't forget velocity is meters per second. So what this means is the marble is here at the end of the meter stick, and at time 0, it's right there at the end, and it's moving instantaneously at 1 meter per second. That's what it means. So it's already rolling. Another initial condition might be that it's rolling the other way, or another initial condition might be that it has a 0 velocity, and that would lead to all different solutions, depending on what we have. So what we need to do is use this information, and this is the relevant stuff. All you need to know in order to get the specific solution to the differential equation is wrapped up in here. So how do you do that? So what you need to do is basically plug this information in here, and so you can do that. You can plug in x of 0 into here. So let's do that. X of 0 at time is equal to 0. Let's plug it in there. So 15, 0 squared plus C1 times 0, because this is time is equal to 0, plus C2, and we're saying that this is all equal to 0. The position at time 0 is equal to 0. This is the position evaluated at time 0. It's equal to 0. So what you can see here, this is going to drop away and this is going to drop away. So what you found from all of that business is that the constant C2 for this specific problem is equal to 0. So let's go ahead and box that because it's going to be important later on. So we found one of those constants. We found one of those constants. Now in order to find the other constant, we need to look at the other initial condition. And that's a condition involving the first derivative, which is the velocity as a function of time. Now, in order to plug it in, you need to have a function for the velocity. Here, this is not a function for velocity. You could take the derivative of this and then use it, but you don't need to because we've already done that. If you look back over here, when we first started our problem, this was the initial problem. We took the integral, we ended up with this. This is the velocity. dx dt is velocity as a function of time. And we found out that it was equal to 30t plus c1. This is the first derivative as a function of time, 30t plus c1. So rewriting that again, I'm going to go ahead and draw a little divider here. X prime of t is just simply equal to 30t plus c1. You could get the exact same thing by just taking the derivative of our answer. 30t plus c1. This is going to disappear when you take the derivative of it. So either way you want, you've got it already done as part of doing the problem, or you could just take the derivative again if you wanted to. So let's plug in our initial condition. X prime of 0, because time is equal to 0. So the velocity at time 0 is equal to 30 times 0 plus c1. And that's equal to 1. So we just took the velocity that we had from the other board, we plugged in a value of 0, and we set it equal to 1 because that's what we said we had. And so for the initial velocity. Now we cancel through this, and so what this means is that c1, that little constant c1, is equal to 1. And I'm going to box that because that's important. So look what we have here. We've calculated a value for c1, the constant. We've calculated a value for c2, the constant. We already know what the general solution is, so what we're now going to write down is the specific solution is, and we're just going to use our guy from up there. So it's x of t is equal to 15t squared plus, it's c1 of t, but we know c1 is equal to 1. So it's going to be plus t, and then it's going to be plus c2 from up here, but c2 is equal to 0, so there's nothing to write down. So this is the specific solution. And all we did was look back at the general solution and plug in the constants. c1 goes in here, so it's just going to be t, and c2 goes in as 0, so it just drops away. This is the specific solution to the case when the whatever it is I'm talking about starts off at location 0, with a velocity of 1. If you change any one of these initial conditions, then the constants are going to change, and the specific solution that you get in the answer is going to be different, which makes sense because if you throw the thing differently, or you start it at a different position, the motion should look different. And it does look different through these little constants of integration, really is what they are. So that is a really good introduction to differential equations. The next section, we're going to work some problems, building upon the material that we've learned in this section. So it's not going to be anything new. We're just going to work a lot of problems here in the next section. The main thing to pull away from this section, really, is that differential equations are all around you, and they're simply equations that involve derivatives. And when they involve derivatives like that, you're still trying to solve for the variable. You're still trying to solve for the variable wrapped up inside this derivative. Now, in this case, we did a very simple example, f is equal to ma, and taught you, hey, that really is a differential equation. And you can, if you do have a derivative on one side of the equal sign and everything else on the other side just involves, in this case, involves a function of time. It was a constant, but it can still be considered a function of time. Then you can just integrate them as many number of times as you need to. You just need to take care to mark your constants of integration like we were doing here. You need to mark your constants of integration. And once you get to the end of the road there, you're going to get a function of time, x is a function of time, and it's going to involve these constants of integration. Now, when you see that you've gotten to that point, then what you have arrived at is the general solution to that equation, because every differential equation is going to have a class of solutions, an infinite number of solutions. The specific solution to your problem is going to depend on how things started, the initial conditions. The initial conditions are going to be given in your problem or in the real world. They'll be given by whatever it is you're working on. You'll know what your initial conditions are, and then you'd be able to use those and plug them in back into the solution that you got to calculate those constants, and to calculate the constants there, and then you'd be able to put that right back into your general solution and get the specific solution, which is the actual. This would be something you could plot and say, okay, my marble's really going to move like this. If I change the initial conditions a little bit, it's going to change its motion a little bit, because obviously that makes sense. It's going to change its motion. But the general form, being that there's a 15t squared plus some other junk after it, the general form is going to be the same. I'm Jason. I hope you've gotten something out of this section. Try not to get too worried about this course. There are going to be a lot of solution methods. Yes, the problems are going to be a lot lengthier than what we've done here, but sharpen your calculus skills, work with me, we'll make it together, I promise you. Let's go on to the next section and practice some problems. Learn anything at mathandscience.com.